I'm fascinated by the idea of a self-replicating robot probe, the von Neumann probe, where a spacecraft goes to a star system, finds the local resources, builds copies of itself. Those copies go off to other solar systems, and within a couple of million years, you have filled the entire galaxy with self-replicating robot probes, and you've explored every nook and cranny of your entire galaxy. And it makes me wonder, where are all the robot probes? Why don't we see them? And are we alone in the universe? Is this like technology not possible? I've been sort of going down a rabbit hole, and I've been surprised to find out there are many groups who are working on various ideas of building self-replicating robot probes that you could, for example, build a factory on the moon that will build a copy of itself, and it'll build a copy of itself, and then you could build all kinds of stuff from these self-replicating robot factories. And the technology is surprisingly close. So my guest today is Professor Alex Ellery. He is the Canada Research Professor at the Centre for Self-Replicating Research. Did you know there was a Centre for Self-Replicating Research at the Mechanical and Aerospace Engineering Department at Carleton University? And he is working on this idea of building a self-replicating robotic factory on the moon. Eventually you could see them on Mars. And it's changing the kinds of technologies that you would use to adapt them to this local situation where maybe you can't take an entire chip fab with you, and instead you've got to work with making your own vacuum tubes and 3D printing electrical motors and stuff out of the local lunar regolith. So it's a fascinating conversation about working with the constraints that you might find yourself with on a place like the moon, and yet still being able to build a copy of a factory that could then build a copy of a factory. It sort of boggles the mind when you think about it. All right, enjoy this conversation with Alex Ellery. Alex, does the moon have what we need to sustain our presence on the moon?
That's actually a very complex question. The answer is yes and no.
Yeah.
Yeah, my work is actually trying to leverage as much as possible from the moon. Almost like if you can imagine the native Canadian, or the idea was to live within the environment, utilize the environment as much as you could, and waste nothing. Most approaches to doing, using lunar resources tend to focus on the idea of bringing Earth-based technology to the moon, and then cobbling some kind of locally made stuff. Whereas my approach has been basically trying to push the boundaries as far as we can to see what we can do on the moon and how much we can leverage it, and sometimes adapting our technology to suit the moon, the resources that are there. So I'll give you an example. An example would be if we want to build electronics on the moon, it's not going to be feasible using current techniques for solid state technology. But we can build computing capabilities on the moon if we readdress how we do it. And one potential approach would be to say, maybe one that I've been looking at, is to utilize vacuum tube technology, because the basic materials are available on the moon. And that means we have to readdress how we architect our computing. We don't have CPUs the size of a block of flats, so we want to try and look at alternative architectures. And one of the architectures I've been looking at has been analog neural networks. So it's developing a new approach to utilize the resources that are there and adapt to the local environment. So it does mean creating new technologies, new techniques for utilizing the resources. There are some limitations, however, and one is that there are some materials which are very scarce on the moon, things like sodium and chlorine, which are extremely useful as reagents. And in fact, one of the relaxations I've put in the way we approach things is, yes, okay, we're going to have to bring reagents from Earth to the moon, but we can recycle them, so we don't actually consume them as such. So an answer to the question, there's yes and no aspects to it.
Right. Well, let's imagine, like, right now today, as we've seen a couple of landers successfully and unsuccessfully reach the surface of the moon, and they are made 100% out of Earth resources by engineers purchasing gear and putting it all together and machining things and so no part of these are made on the moon. But if we imagine, as we transition to going from everything being made here on Earth and being delivered to the surface of the moon to some future, as you may be imagining it, where suddenly or eventually every component of the spacecraft, lander, rover, research station, whatever, is built using local lunar resources. What does that transition look like, do you see? What's the low-hanging fruit to start with and then shift into more and more complex parts of the task?
Well, it's interesting that because there have been two main approaches to employing things like self-replication on the moon. One, which is supported by some guys at NASA at Kennedy, who've been suggesting that once we reach a certain stage of industrialization on the moon, we can then start to retrofit self-replication onto pre-existing structures and capabilities. I would argue the other way. I would say part of the problem is that when you try to create a self-replicating machine, you have to ensure that the self-replication loop is closed. What that means is that the everything that's in the self-replicator has to be replicated, and that's actually very difficult to do. And you have to employ a certain amount of ingenuity to do that. So my approach is essentially to approach it in almost like the origin of life way, which is we don't really know how life really originated, but we know it must have evolved from the ground up from the local resources that were available. So we have to essentially emulate the same thing. So we have to work with the local resources that are available to us and utilize only those resources. We also have to ensure that things are simple enough that they can be replicated. So the idea of retrofitting doesn't really work, because what you're doing is you're taking a complex system and then you're replacing it with something simpler, which has reduced functionality. So that's not really the approach I would take. Basically, this is an all or nothing thing. So when we build a self-replicator, we have to figure out how to build the self-replicator, build one on Earth, and then send it to the moon, and then get it to utilize the resources that are available on the moon.
But is that even possible here on Earth? It's funny. I issued a self-replicating challenge a couple of years ago to see if anybody could. I said I want to watch a robot make another robot, and right now at our current level of just knowledge, industrial capability, even if you make the most, you're here on Earth and you can shovel dirt and material towards the robot as needed. You can plug it in and it can get its electricity. You can give it all kinds of jump starts. Would we be able to have a robot make a copy of itself here on Earth?
It doesn't make a lot of sense to do it here on Earth for two reasons. The first reason is economic. It would have to compete with. We have our entire economy and technology system is self-replicating in essence in itself. So to replace it with a smaller machine competing with a current capability doesn't make a lot of sense. The second reason is that ultimately a self-replicator has to use local resources. The Earth is a very complex tectonic environment, which is basically weathering processes, redistributed resources all around the Earth and concentrated them in certain locations. So a self-replicator manufactured for one location can't be translated to a new location because it have to be redesigned to utilize the new location.
But I guess I'm asking, like, if you put it in the ideal situation, if you put it in a Best Buy, or you had it in a pile of Lego bricks, or you had it in a junk pile, or whatever is the most ideal situation possible that you can possibly imagine for a robot to try and build a copy. do you think that we could do that here on Earth?
Yes. Essentially, if you had, let's say, let's take your junk pile, let's say, so piles of metal of various different types that you need. Yes, you can, and I can envisage that would be possible, and we'd need to develop something like that, which is adapted to the geology of the moon, to apply it to the moon. And so I've been focused on the moon, which has a limited resource availability in terms of materials compared to Earth. But this actually turns out to be an advantage, because if you can imagine you got your mobile phone, for example, there are about, I think I remember reading, there is something like about 60 to 80 different materials in this phone. Each one of them has to be mined and then processed. And so there's this huge fan-in to making this phone. In order to close the self-replication loop, we need to narrow that fan-in as much as possible to minimize the amount of processing that has to be wrapped into that self-replication loop, then minimize the amount of mining, minimize the amount of materials processing, and even minimizing the types of manufacturing machines you need and assembly and so on and so forth. So what this means is that we want to minimize the number of materials that we use. We want to minimize the number of parts that we manufacture, and also we want to minimize the amount of energy we need, and minimize the amount of information to specify all this. Now, you talked about energy a few moments ago. The way I envisage going to the moon is we send a seed machine, maybe about 10 tons, and then it grows by growing its energy capability, its energy capacity, by building more and more energy solar stations. And then it grows to its full extent, and then it has enough power to replicate itself. And it will replicate another seed, and then that will grow, and so on and so forth. So the idea is that it's self-replicating in its entirety, but it has a maturation stage. You've got seed, and then it matures, and so on. So that way you can handle the power aspect relatively straightforwardly. In terms of like Earth, yes, we can build something like this. And I see no reason why and in fact, my goal is to build a demonstrator on Earth, and then, basically send it to the moon for, and then adapt it.
Yeah, I mean, it makes a ton of sense that you put it in a sandbox with all of the local resources that it might require, and then find out how it goes wrong, and then fix that problem either by giving it the better resources or changing the plan. So I want to talk about it at like broad strokes, the different components. We talked about power. I'm sure you talked about chips briefly. So what are sort of the major components that you have to think about? And I'd be interested to sort of hear what are the lunar analogs to those things. So let's start with power, for example. So how do you make power on the moon?
Okay, let me answer your first question first and then lead into that.
Sure.
So the key to making it work, I remember I mentioned about the types of parts you need, minimizing the types of parts you need. We want to get a lesson from biology, and this is something called exaptation. Exaptation is where feathers first evolved in dinosaurs for thermal insulation, and then they were later adapted in the offshoot we call birds for flight. So it's a case of where one capability had evolved and then was adapted to a new capability. So I've taken very much the same approach. And so going to power, for example, one of the constraints I've had is how do we minimize the numbers and types of parts that we need? So I've looked at various types of power systems, and what I've tried to do is start off with what do we need to create a robotic machine. So the two main types of components we need to create a robotic machine are an electric motor, which basically provides actuation, and that can be applied to any kind of actuation. And we also need something to implement some kind of electronic amplifier. Now, transistors we can't use, but vacuum tubes we can. But a vacuum tube itself is a thermionic device. So that provides us with the capability to convert heat into electrical energy. So if we combine, let's say, a Fresnel lens, which generates heat from solar energy, focus that onto a thermionic converter, we have electrical energy. So that's the approach I've taken with raising power. We utilize the same components that we utilize for other things. Similarly, for example, another piece of the puzzle that we need for a robotic machine is sensors, and the most important sensory modality is vision. How do we create vision systems? And the approach I've taken is to look at things like photomultiplier tubes, which are basically vacuum tubes which are sensitive to light. So what we're doing is we're taking a particular type of device, a particular type of art, the vacuum tube, and adapting it for computing, for energy generation, and for vision. So it's basically adapting the same type of device for multiple applications. And the same with a motor. For example, you talk about energy. Well, during the lunar night, we're going to have to store energy. How do we do that? Most people think about batteries. But one other possibility is flywheels. And flywheels are basically motor-driven rims. So again, we're adapting a single type of component for multiple different applications. And that, to me, is really the key to actually closing this self-replication loop.
So does it, like, if you just keep coming up with ways to combine components together, are you saying you just end up with vacuum tubes and some kind of electric motor? Is that?
Yes,
is that like the bare minimum?
We'll also need various materials. So if you take the breakdown of a spacecraft, you need structure, you need thermal insulation, you also need electrical conductivity. So on Earth we use copper, but we can replace that with aluminium, for example, which is actually there's quite a lot of aluminium on the Moon. So we also look at it from a materials point of view in terms of the functionality of specific materials, but also as components. But the two things together, where we're looking at the individual materials and the specific components, we can combine them to create, with just a few other little bits and pieces, I think, to create this full self-replicating system.
Now, when I think about vacuum tubes, I mean, that is however many technology generations back from what we currently use with transistors. What is I guess, like, how much data do you need to do this work? And how much, what kind of, I don't know, processing speed could you get from arrays of vacuum tubes?
Well, remember, we were using vacuum tubes in a slightly different way to the way you would use them in the CPU. So a neural net, an analog hardware neural net, actually has the program actually in its hardware. So it's very fast. The second aspect is that one of the things we're looking at, you're presumably familiar with the way AI has been going over the past 20 years. They've been using these deep learning neural nets, which are huge and they require enormous amounts of data. One of the things, now there's a limit to how far we can go with that technique. And I actually think, and I'm not alone in this, that actually this is a dead end. And we need to reassess how we approach AI. And one of the techniques that I'm interested in looking at is taking neural nets and building them in hardware. Perhaps we might use spiking neurons, for example, to try and enrich the dynamics of neurons. But we want to minimize the amount of information that we need to store. Now, there are two ways to do this. One is to have dedicated programs, which have their own individual neural nets, essentially. Another technique which we're exploring is to attempt to implement symbol processing in neural nets. Now, this is actually it's not a new research area. It's been around for a while, but it went through a big dip for quite a few years. And because of the problems encountered in these very, very large neural nets we have now, there are now some research groups who are actually interested in seeing how we can compactify neural net representations. So that's an area of research, I think, which we're forced to go down this road uh, in terms of like a self-replicating machine.
Right. If we ran a GPT-4 powered robot that had the appropriate training and put it on the moon, it seems reasonably straightforward that it could reach the point that it could carry out these kinds of tasks autonomously without failure. And so I think we're at that level technologically with our current, and this is brand new. I mean, we're only seeing this kind of dramatic jump in robots being able to carry out these kinds of tasks, put the blue box in the red drawer and open up the bag of chips and deliver it to the red pony, whatever, right?
Yes.
This stuff is all brand new. But if you sort of think about minimizing, like once you've decided, okay, this is the absolute bare minimum functionality that's required, we're going to use a neural network, we're going to embed it into vacuum tubes, and then we're going to just cut away all the fat until it is the absolute bare minimum to bootstrap up this process. Is there a amount of memory that you sort of envision that people could sort of wrap their minds around?
Yeah. Okay. Let me give you an example of some of the difficulties in terms of like the amount of information you need to specify a self-replicator or any kind of structure or machine. If you look at a 3D printer, you got your sort of like your CAD model, and what the CAD model is basically a set of Cartesian points, and you slice it through the middle, and then you feed a sequence of Cartesian points to create your layered structure, one on top of the other. That's a very information dense approach. So one of the things we're starting to look at is, instead of taking your CAD model and slicing it into slices, you can do that, but let's change the way we specify it. So what we start off with is a set of initial coordinates, and then we have growing rules. And growing rules are actually very simple, so we can grow the structure. So we don't have to specify the Cartesian coordinates at each level. So we grow the structure using these rules, and then we simply store the rules.
That sounds very familiar to life, doesn't it?
So, well, yes, it's basically a form of growth. So it's basically growing. It's essentially how anything grows. An embryo grows in essence. And so it's basically forming. We're actually implementing a form of information compression. So that way we can reduce the amount of information need to store the specification of the entire system. How far we can go down that road, I don't know. But a lot of the inspiration I get is actually from biology, looking at biology, how biology does things, and then seeing if we can emulate that in some fashion. Obviously, we know biology works because we exist.
Yeah, I mean, there are these. I know that in certain genes will define various attributes of an animal body. In many cases, it's just expressed in an extremely compressed thing that you just change one gene is defining how long the legs are, or in many cases,
it's also the control genes as well. So, for example, a lot of growth is basically through timing signals. So you grow, and then you grow for a certain time, and then the gene switches off, and then it stops growing. So you just need a representation of time in order to create the shape of growth that you need. So these are all things that we can explore to try and minimize the amount of information we need to store to actually replicate something. We want to replicate an entire machine.
So, we've spent a lot of time on the vacuum tubes. So let's talk about the motor.
Yep.
That sounds challenging.
Okay, well, that. We haven't 3D printed a vacuum tube. We have 3D printed an electric motor. So we used several different techniques. We printed the magnets. We printed all the other parts. And we assembled it by hand, obviously. The hardest part was the wiring, the wire coils. But we've demonstrated we can, in principle, 3D print an entire electric motor, which we feel was, or I feel is a significant step towards demonstrating that 3D printing, either by itself or supplemented with a small number of other types of manufacturing machines, essentially can construct virtually anything. And when I say anything, what I mean is that if you construct any type of machine, all machines are basically different kinematic configurations of electric motors. So a robot arm is one type. You've got a lathe is another one. A milling head is another type of kinematic machine. So once we have electric motors, we can then create new types of machines to do whatever we want to achieve. But the core of it is the 3D printer, which is essentially a Cartesian robot. It has a moving head which moves up and down. So it's a Cartesian robot in essence. So the idea is to try and, minimize the types of machines we require. And we've demonstrated that we can print electric motors. And eventually I'd like to print some kind of vacuum tube type device. But that will come later.
Right. It's interesting. Well, when you think about, like, this is going to sound like a really weird tangent, but when you think about, say, topology, that you have things are either spheres or donuts with multiple holes. And so when you really take the pure essence of all of these different machines as you describe them, in the end, it's a motor. It's a motor with stuff connected to it that is making the motor work in different angles, different directions, using belts, pulleys, size, scale, speed, all of that. And so if you can make one motor, then theoretically you can make every flavor of a motor just by adding extra things to the outside of it, or changing the size, the shape, the speed, the torque, whatever. And then on the flip side, you've got, like, and these are like the irreducible components that you have to consider. And then the other one was the you need some way to have information flow around. Are there any more, like, just base components that there's no way to get away from, do you think?
Yeah, I'd say the other one, which we have them in our lab, but we haven't actually tried to manufacture them, and that would be Fresnel lenses. They will be, I can see them being quite challenging to manufacture because of the etching on the surface. Fresnel lens is basically a flat lens where you replace the shape, the refracting shape, with a series of etches which emulate, basically to, like, focus the beam as a lens would do. That's potentially very challenging. We haven't really addressed that yet. We use Fresnel lenses in our labs to use solar energy to melt metal and stuff, but we haven't actually tried to manufacture one. Potentially, we could replace them with mirrors, which would be a lot easier to do, some kind of parabolic mirror. But we haven't really gone down that road yet. So I'd say that's one thing we haven't tackled yet.
I mean, I interviewed somebody a couple of years ago. They were looking to build a lunar rover, and they were going to manufacture solar panels on the surface of the moon just by scooping up regolith, mixing in various ingredients, and then laying down a film as the rover goes. And I guess like a version of like perovskite or some kind of solar cell material. But I guess you're limited by what your self-replicating robot is capable of producing, not necessarily what a sophisticated manufacturing robot could produce out of those same lunar resources.
Well, I would argue that this solar cell printing robot, I'm pretty skeptical. I'll tell you the reason why. Yes, there's a lot of silicon on the moon, and yes, you could use basically create. You can certainly create glass quite easily on the moon. The question is whether it's actually transparent or not, because there's a lot of iron in it, and iron darkens glass. You could also potentially extract silica to create fused silica glass, which would be transparent. The problem, and then you'd have to reduce that silica into silicon itself to create the problem becomes with the dopants. And not just the dopants. It would be you have to create a solar cell. You need something called a PN junction, and that's where you get two pieces. Well, you get a single piece of silicon. They've got two parts to it. One part is doped with some kind of what they call a P-type dopant, and the other one is doped with an N-type dopant. So you have to control the diffusion of those dopants through the silicon, and that takes a lot of precision. Otherwise, the solar cell you're going to end up with is going to have a conversion efficiency which is so poor, it's not going to be worthwhile. I would say you'd be lucky if you get 1, 2, 3% out of it, conversion efficiency, which is, you need a huge carpet of these things to get anything useful out of it. Whereas with thermionic conversion, you can get 10, 15%, and potentially even as high as 30 or perhaps even 40%, depending on how you cascade it with other techniques. So I would argue that I believe that the thermionic conversion approach is actually a better one, and I think that printing solar cells on the moon is a lot harder than people think it will be, and actually the resultant solar cell will not be very, very efficient.
Right. But I guess if you're looking to bootstrap, then you're not incredibly concerned about the efficiency. It would be great, but if you can even just get to the beginning, that's a big step.
Yes, I think it assumes that we can print a large carpet. There are also other things, of course. All these cells have to be connected, so for that you do need to use metal. Now, aluminium you can do that with, and aluminium we can extract from the moon. I can see how it might be done, but I'm still questioning the efficiency. But which is the reason why I went for thermionic conversion, because we need to have a highly efficient system.
Right, and I guess the point being that you've already got these photoreceptive vacuum tubes that you're already having to build, and they can serve double duty. So
yeah.
So let's sort of put this all together and take me through what would be the mission. Like you've done it, you've made the prototype work here on Earth. You're able to produce a copy of a copy of itself. You feel comfortable. You buy a ticket to the moon. What goes to the moon, and then what happens next?
Okay, you'd have this self-replicating seed. So basically, it'd be a full manufacturing unit without all the power parts required. You'd have some power, but not the full capacity. So that would then get plonked onto the lunar surface.
And like, how big would it be?
Sorry?
How big?
I imagine it rather like a fairly large lorry, articulated lorry.
Right, in the tens of tons range.
10 tons, 10 to 20 tons. So fairly significant. But we would need about 100 tons to create all the kind of like the additional power raising stuff that we'd need to go with it. It's complicated by the fact that we also have 2 weeks of night on the moon, so we need to store power for the nighttime as well.
All right, so you've landed this 10-ton thing onto the moon. What does it look like? Okay,
so it has several pieces to it. So you can imagine if you can imagine like a shipping container, I suppose it's like inside it will have various pieces of unit. So it'll have a set of rovers which will scoop up regolith, and then that will put those onto a set of physical processes. And the first set of processes would be some kind of ball mill. We've done some ball mill experiments in my lab. And then we grind it so that each piece is the size of a single crystal, single mineral. And then what we do is we separate out into different pieces. So we use magnetic separation to separate out some of the iron and stuff like that. And then we'd also use electrostatic separation to separate out various components, to separate things like felds, from anorthite from ilmenite and so on and so forth. And then we would have a set of chemical process. In fact, just 3 sets of chemical processes. So one of them would be HCl leaching, which we've demonstrated in the lab. We've taken Highland simulant and extracted silica out of it and extracted alumina. So that would be the first stage of processing. And so we'd keep things like silica because we want to create glass. So we can get pure glasses out of that. And glass has many, many different types of uses. Where I did my PhD, the whole library was made out of glass, including the steps and everything. So you can do quite a lot with glass. The alumina, alumina itself is also extremely useful. It has properties second only to diamond. It's very hard. It has a lot of very useful properties. But we can take some of that alumina and then we can reduce that into pure aluminium. So, and that's actually something we're currently building as an electrolytic unit to actually reduce alumina directly into aluminium. One of the other things we also want to be able to do is take this aluminium, we want to be able to mix it with other additives. So we might want a little bit of iron in there. I know what we want. We want some nickel and cobalt to add into the aluminium to create alnicomagnets. We also want to create electrical conducting wire. We want to create structures. So these all require different alloys. And so what we're looking at the moment, we're working with NRC to see what kind of alloys we can generate from lunar resources and what their properties will be. So, for example, quite often we add chromium to metals to make them resistant to corrosion. But we don't have corrosion on the moon, so that's something we don't need. So we can adapt what we currently use. And again, this goes back to this idea of adapting to the local resources we have available to us and the conditions we have on the moon. And then we can 3D print this aluminium into either structures or utilize it as part of a multi-material object, like an electric motor. So the idea is to in this package, you have, the final bit is basically the 3D printing with an assembling system in there. So that's the core of it. The rest of it also has some power raising pieces in there as well. And you'd also have all your electronics and stuff like that as well. And that would be landing on the moon. And the first thing it would start to build its capacity, its energy capacity. And then it would build a copy of itself piece by piece using motors as components and vacuum tubes as components, and then start and just basically build it and then build it right next to it. Ad infinitum, effectively.
Right. Well, I mean, that sounds awesome and also pointless if it's just going to build copies of itself. I mean, apart from, boy, that's cool, it can build copies of itself. Where does this become practical for what humanity might want to do in space?
Right. Okay. So, animal, or any kind of creature, their genes are basically can build any kind of creature depending on the configuration of the genes. The same thing is true with a self-replicator. Now, going back to the John von Neumann, who was the original architect of self-replicating machines, one of the properties of a self-replicating machine is that it's based on something called a universal constructor, which means that it can build anything within reason. So if we can build a self-replicating machine, we simply change the program that's stored to build anything we like. And pretty much anything we like, we can build any type of machine because we've got motors, we've got control electronics and anything. So we have the capacity to convert what is in effect a general purpose. For each of these self-replicating machines is a general purpose factory. It's a question of how we change the program to build new products. So in effect, when we're growing this capacity, what we're doing is we're growing general purpose productive capacity.
Now, you've been doing your thinking about the moon. How would this be adapted to other worlds? What about Mars?
Yeah, in some ways, Mars is easier because Mars has materials that we don't have on the moon. One of the problems with the moon is that there's very little carbon, which means it's very difficult to manufacture things like plastics. On Mars, there's loads of carbon. It's in the atmosphere. So we can simply extract that, convert it into methane. In fact, through the Sabatier process, and that actually was demonstrated couple of years ago on Mars. So once we have the feedstock, we can then create other types of plastics and so on. So we're on Mars. It's actually a little bit easier. Where it becomes a little bit harder is that aluminium is less easy to get access to. So, but again, we can substitute. There's lots of iron as opposed to aluminium. So we can make this trade relatively straightforwardly, I think, for Mars.
And then other places in the solar system. I mean, like the classic, I think, is going to the asteroids.
Yeah, asteroids. Yes, one of the problems we have is on the moon. We do need metals that are plentiful in asteroids, but not on the moon. It's reckoned there are some potential ore bodies located under the surface of the moon where Nicoline meteorites have basically landed on the moon without breaking up, and potentially we could access those asteroid materials. So you could, in theory, practice asteroid mining on the moon without all the zero-G difficulties that you're going to have. I've recently in fact, I'll be presenting actually in a month or two a paper on, well, if we can't find these ore bodies, what do we do? Because they're completely floors us if this is the problem. So one of the things I've been looking at is how to move an asteroid, a Nicoline asteroid, and land it onto the surface of the moon. And what we do is we use coil guns, which basically scoop up the material and eject it as to get rocket thrust. And basically, you use up about 2/3 of the material, moving it to the moon and landing on the moon. But we still get about a third of it landed on the moon, a soft landing. So, yeah. So in a way, part of that lunar concept is to look at asteroid mining and to develop asteroid mining. The most challenging part of asteroid mining is the fact that there's very little gravity. And so virtually everything you want to do, from drilling to moving around, requires you to have some kind of hold down mechanism because you've got no gravity field at all. And that presents a real challenge.
But it is easier to escape the gravity if you want to send it somewhere else.
But to me, that's trivial. That is, I would rather have a heavier gravity field and have to use fuel to get out of it than this whole idea. The whole infrastructure around an asteroid has to deal with this very, very challenging problem of staying on the asteroid. And that is, to me, is harder than going to a gravitating body and utilizing the gravity that's there and having to launch off. I mean, the moon is 1/6 G. That's a relatively modest gravity field. I'd much rather have that than doing things on asteroids, because asteroids, it's just so difficult to stay on it. And all the machines that you need to have some kind of reaction. They exert a reaction effect on the machine.
That's interesting, though, because I think when we wonder about where the alien factories are in the solar system, where the von Neumann probe factories are, the instinct is to look to the asteroid belt. But if I understand correctly, you're saying the best place would be on the moon. We should be looking for a gigantic self-replicating robot facility on the moon or on Mars.
I would say that if some kind of extraterrestrial intelligence was capable of interstellar flight, they may have ways of dealing with asteroids that either we can't do or we find too difficult, or we just haven't got the experience. A lot of it is basically we learn by making mistakes. We learn through experience. So once we've actually gone to asteroids, then we'll probably develop the experience and the techniques and so on. So I wouldn't necessarily say that's wrong, but if a von Neumann probe came here or was here, I would probably still expect it to be parked in the asteroid belt, because that provides you access to a whole host of materials that you can't just get on the moon. You got things that you got carbon as well, carbonaceous chondrites, you got water, you got ices and things like that, which as well as all the metals. So you've got pretty much everything you need.
Yeah. You can go shopping in the asteroid belt to find the asteroids that have the bits and pieces that you require.
Yes, yes, indeed. And they're all mixed as well. So you got like some which have some of one, some of the other, and so on. So yeah, you could shop around quite nicely
And
there.
I mean, what I like about this, what you're working on, is that it's very practical. I mean, what is the minimum viable self-replicating machine that we can possibly make and have it be off planet? But this theoretically will fall under an exponential growth curve with miniaturization, with new technology coming through. Where do you think this logically proceeds over the decades and maybe even the centuries and millennia into the future?
Well, there are two things. First of all, my goal pursuing this, what I want these machines to build once they've replicated themselves, I want them to build solar power satellites. So we can build solar power satellites on the moon, put them into orbit around the Earth, and provide clean energy to the Earth. And we could do this once we have self-replication technology, and we do it on the moon. What we're effectively doing is we're doing two things. Firstly, we're making space exploration, space colonization directly relevant to every single person on Earth, and affecting their lives on Earth, providing clean energy. The second aspect is that it actually effectively offloads the entire energy generation business or industry onto the moon, and thereby relieving the Earth's biosphere of that particular industry. Beyond that, I think that once you have self-replication capability, that it opens up the entire solar system and eventually the stars. There's no doubt, I actually believe that the only way we are going to go out, I mean, you look at history, we landed on the moon in 1969 and never went back there. Maybe we might be to get there for the second time next year. Spaceflight has not been made relevant to people. And we have to make it relevant to people to actually get people to go out there, to make it important for people. If we put self-replicating machines on the moon, we have productive capacity. We have assets. Once you put assets somewhere, now you've effectively lowered the barrier to commerce. And so I'm sure people will invent ways and find ways to make money out of this kind of capability. Once people figure out how to make money, then the people will follow. And I think, again, we can use the same approach by going to Mars and beyond to other moons and planets and whatever, to become, a solar system-wide species. So I do think it's really the only way, because it's the only way we could do it at low cost, or minimal cost, should I say. And then, of course, eventually we're going to start thinking about, well, if we could do this in our own solar system, maybe we could send out von Neumann probes to other stars within our galaxy. And effectively, and again, if you crunch the numbers, you could cover the entire galaxy with self-replicating machines in about 1 million years, which is a very short space of time, astronomically speaking.
Right.
And I think actually is a powerful argument against the existence of extraterrestrial intelligence, because we haven't found any.
I do as well. That the fact, like, the question is not why haven't we heard signals from alien radio transmitters. The question is, why isn't the solar system filled with von Neumann probes sent by various species throughout the Milky Way? I mean, I guess I've got sort of like two timelines. So I guess the first time is like, when do you think, based on what you're working on, that first robot factory creates a copy of itself? And when do you think we send out that first one to another star system? Or when will it arrive? When do we get a copy of a robot factory in another star system?
Okay, so there are two questions there. The first one, if I had the funding that I needed, I reckon we could get the first prototype self-replicator working within about 5 or 6 years
Wow.
on Earth.
Right.
Then it would take a few more years to get the first prototype to the moon. But the advantage of a prototype is that if it works, if it is truly self-replicating, it basically can be reprogrammed. So if it goes wrong, then we simply set up a new program to change whatever it's making. So as long as the first one works, or we can get it to work sufficiently well, then we can correct it without setting up new machines. So that, again, is a very cheap way of doing it. It's much cheaper than setting up new machines and trying them out and testing them out. So I would say that I think once we've created a population of these machines on the moon, that would be relatively quick. Because once we've got one or two on the moon, and then you've got this geometric expansion rate, then you could basically have 1 million units within 13 generations. And if each generation takes a year, it takes 13 years. So very quickly we could have industrialized the moon once we've developed the technology. From the von Neumann probe perspective, I would imagine that once we have this capability and it effectively opens up people's minds to interstellar flight, I think, because we've got the payload already sorted out. I don't think it would be that long, because once we have the capital, what do I call it? It's like the machine capital on in extraterrestrial environments. It's relatively cheap to try and build things from local resources. So we could start building starships relatively cheaply, I think, once that happens. And then, well, it depends on how successful we are in developing some kind of propulsion system.
Right. That's someone else's problem.
Yeah.
Yeah. So, Alex, I think one concern that we have is, here on Earth, if you just talk about exponential industrial progression, this runs directly into our environment about how we treat planet Earth. Mm-hmm. And so when someone thinks, within 13 generations, you've industrialized the entire moon, that starts to sound awful. So how do you think about sort of preservation of the wilderness, of the environment of the solar system in this sort of exponential growth of industrialization?
Yeah. Okay, there are a couple of things, a couple of points in there. And I think, first of all, we look at sustainability. Now, yes, you're quite right that exponential growth can happen, but within one of the requirements for self-replication is sustainability, because you have to close this physical loop and the energy loop as well. So that forces us to do things sustainably, or as sustainably as we can. The second thing is that I'm not mining water, which is a scarce resource on the moon. In fact, I'm actually not in favor of doing this, of mining water and then burning as propellant. There are plenty of other uses for water where we can recycle it. So burning water on the moon as propellant, I don't think is a good way to go down that road. The second, so what we're working with is common rock-forming minerals. They're everywhere, and even 1 million units is nowhere near exhausting that resource. It's a drop in the bucket, as it were. So from that perspective, as long as we control the growth or limit the number of generations we build, then there's no problem there. Now, that of course requires us to control that growth, that replication. So I actually wrote a paper on this, suggesting that there are various things we can do. One is to implement a 2-layered kill switch. So
I think I reported on this.
Right.
That we need to shut these things down at some point.
Yes. So again, what appeared to be a disadvantage was that we had to take salt from the Earth to the Moon. That is essentially a salt contingency. So if we deny salt, it no longer can replicate. The second kill switch is actually on the Moon, which is located where the asteroids are, either the ores or where we put asteroids. So that we need all the nickel and cobalt from there, and selenium and stuff like that. So that also acts as a kill switch because we can shut that off, that supply chain off. That's how we deal with it locally. In addition, we also want to implement something like a Hayflick limit. A Hayflick limit is a biological limit to the number of replication cycles a cell goes, and it's based on telomeres. These are kind of like the ends of DNA, and they get chopped off. They act like a counter, a program counter. And we can implement a similar kind of approach for a self-replicator. So we actually implement so that within the coding system, we have a set of telomeres essentially, and they get chopped at every replication cycle. And you can arrange that physically so that when your reader goes to the first point, that isn't replicated. And so what it does, it's only reading stuff downstream. And so every replication cycle that gets shorter and shorter and shorter until it starts to chop the code itself up, and it can't replicate anymore. So that's another approach. And then of course there's the approach which is used in communications, satellite communications, spacecraft communications, which is error detection, correction coding. We use this for memories and things like that in space and so on. So this is a very well established technology. So the implementation of all these different techniques allows us to provide a multi-layered defense against grey goo or runaway.
Yeah, just turning the entire Milky Way into self-replicating robot factories. Yeah, that's really interesting. I mean, exponential growth has a way of getting away from you, and we see this with pandemics, with all kinds of bacteria, infections, all kinds of things that but letting something.
This is an engineered machine, so this I would argue it's hard enough to get the damn thing to work, let alone having it going running amok and everything. I think that's for me, from my perspective, that appears to be very unlikely. But we can implement all these safeguards to ensure that doesn't happen.
So what about self-assembly? How do you implement that? So
the self-assembly thing is basically I want to create a module, a self-assembling module. And most people have created these modules which self-assemble into structures and so on and so forth. But what I want to look at is the actual module itself. So I want to incorporate I want to 3D print an entire module. So this would demonstrate again the 3D printing of a modular robot essentially. So we've already 3D printed the motor aspect. The next bit we want to print is some of the electronics and some of the sensors. So and some of the latching techniques as well. So the idea is it's a step beyond the motor to prove that we can 3D print other aspects and package it into a single module and create a reconfigurable robot type of thing. So it's basically a variation on that same theme.
Right. Well, Alex, it's been a pleasure to talk to you. I look forward to the first self-replicating robot factory on the surface of the moon, and hopefully a limited number of them filling the universe with grey goo. But it's fascinating to think. Like, I think this is the inflection point, that if we can crack this problem, then we can bring the resources of the solar system to us in a way that enables us to continue our existence here and not have to draw upon the resources of planet Earth anymore in the way that we do. Like, This is the way that we become more sustainable to planet Earth. And I'm interested to sort of see how this all plays out. Good luck.
Thank you very much. It's been a pleasure.
I hope you enjoyed this conversation with Professor Alex Ellery. I'm going to give you some more of my thoughts in a second, but first I'd like to thank our patrons. Thanks to Stephen Filer-Munley, Paul Rohrbach, Abe Kingston, Hey Twyla, Dougie Stewart, Stephen Krasaki, David Richards, Mark Anstis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Shiplin, Modzo, George, David Gilton, Andrew M. Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I think this comes to the heart of, for me, the most powerful answer to the Fermi paradox, that we are first or we are alone in the universe, because we are getting to the point now within a couple of decades that we can start building self-replicating robot probes here in the solar system. And over time, as the technology follows this exponential curve, we will build smaller devices, they will replicate faster, and eventually we will send these things on a journey to the nearest star systems. And when they get there, they will make more copies of themselves, and then they will move on to the next star systems. And so if this is a thing that we are right on the cusp of being able to do, then it stands to reason that other advanced civilizations across the Milky Way have done the same. And no matter where they start out, within a couple of million years, they will have essentially visited every single star system in the entire galaxy. And where are they? And so the better we get at building self-replicating robot probes, the more troubling and weird the Fermi paradox becomes. And I am excited about the technology. I'm looking forward to what we can possibly accomplish as we expand out into the solar system and become a true solar system civilization. All right, I've done some interesting interviews with the ways that you might move to other star systems, maybe not at the speed of light, but as fast as possible to make the journey within a single human lifetime. So check those interviews out. All right, we'll see you next time.